Hello, everybody. Welcome to my talk from large language models to reasoning language models, three eras in the age of computation. My name is Torsten Höffler. I'm a professor at ETH Zurich. I've been focusing on high performance computing for the first half of my career, and now the second half of my career, I'm focusing on artificial intelligence, very large scale systems, large language models, but also language models that could apply to climate and other health applications, for example. So today I want to talk about these three eras of computation in the age of computation. But I want to start very early on, where we in humanity went through the Stone Age, the Bronze Age, the Iron Age. So this is more like a joke, as you can imagine. But we also went through construction manufacturing. We invented Roman technology, we invented medieval technology, we invented Renaissance, and at the end, the Industrial Revolution, just about 200 years ago, less than 200 years ago, actually. But there was one interesting change at the end of the Industrial Revolution. And that is really that human physical strength stopped being relevant. Humans were able to operate pretty large machines, massive machines, ships, airplanes, tanks, sadly. And they were able to operate them in a way that the human strength was not needed anymore. So now I want to go forward from here. So technology. So we went into the atomic age, we went into the space age, and we went into the digital revolution. That's something that I still remember when we all suddenly had more and more powerful computers, decades of Moore's law scaling, giving a more than 1 million times improvement in compute performance. And then we learned to connect these systems to each other. And that was quite powerful. We created the internet, we created a World Wide Web that was enabled us to collect all this data that we generated in the data age. And this really, in the development of intelligence on the planet, we are the species that can communicate thoughts without experience, but we can communicate thoughts through written language, through spoken language, through images. And this is really what culminates in the digital revolution, together with the information age, where we connected all of those now into the data age. Many people claim that we're actually currently in the data age itself, but I would claim we have already left the data age. But now I want to pose the question for the remainder of the talk. I will not really answer it, but I wanted to pose it for your entertainment. When will human creativity and intelligence become irrelevant, like human physical strength stop being relevant? So it's something for you to ponder. But I want to also stipulate that we are already beyond the data age. In fact, we are in the age of computation. We're in the age of growing compute capabilities that allow us to generate data. So let me substantiate this a little bit. You're probably familiar with this company, NVIDIA. If you learned about a year ago, you definitely have learned about it the last couple of months big time. And this company is a very fascinating company. If you look at the market capitalization, 10 years ago in 2015, it was literally a $0 trillion company. Today, in 2025, it is more than a $3 trillion company. So it was the company that has the largest growth or the fastest growth in human history, and it was the second largest company today. So it was very, very close behind Apple before what happened last at the beginning of the week that I will also talk a little bit about. So this company makes compute accelerators and networks, but not data storage. So it's clearly building on just fast compute. This is why this is one piece of evidence why I'm claiming that we're in the age of computation. Another piece of evidence is basically Sam Altman saying that, and he said that nearly a year ago, that OpenAI generates about 100 billion words a day. All people on the planet speak about 100 trillion words, so just 1,000 times more. That was a year ago. The adoption of OpenAI and many other AI models, large language models, has been rising exponentially since then. It's been very rapidly growing. So probably today, we already generate more words electronically with computation than we generate through our biological systems in our heads. So that is fascinating, which of course means that we'll be running out of data to train these models on. If we assume that we train these models only on human-generated data, only on biologically generated data. But now the nice thing is we can actually use synthetic data or electronically or computationally generated data for training these systems. So these systems can basically talk to themselves. And we believe, or I believe, that this synthetic data could be better than real data because it could surpass human intelligence, could surpass human thoughts. It could be moving much faster than humans are moving. In fact, it has a much higher bandwidth today, even. So now, if we want to build an AI scientist, and people claim that they've already built one, this scientist would need to create new knowledge that goes beyond the scope of human knowledge. Because, for example, in German, a scientist or science is called Wissenschaft. This literally translates to create knowledge, and it implies that it's creating new knowledge. This is something where we need to go beyond just learning to imitate humans, to just learn to parrot. And this is the revolution that is coming very, very soon. So we have contributed in my group under the leadership of Maciej Vesta, the graph of thoughts idea, where we really make one significant step into this direction. How do we build systems that can learn completely by themselves going forward without much human supervision and use that computation that we have? So that's going to be the remainder of the talk, a little bit of history from large language models and how we go to these systems that can improve themselves over time. Fascinating. But really what I wanted to point out is that computation is the new oil, because all of that requires computation. And one nice fact is, since I'm Swiss and also a professor in Switzerland, we now have oil in Switzerland with this ALPS system. And so this ALPS system is one of the largest computers, if not the largest computer for open science, open artificial intelligence research in Europe. It's an extremely powerful machine with nearly 11,000 Grace Hopper GPUs. Okay, so now if we enter that age of computation, but what just happened yesterday, a couple of days ago? So a couple of days ago, NVIDIA's stock was losing nearly $600 billion as essentially people realized that DeepSeek, a Chinese startup model, was released publicly and was actually performing nearly as good as the large players at a much higher performance, much lower cost. And that was quite impactful to the stock market. I believe this is a little bit overblown, but as usual, the stock market is reacting to all kinds of symbols and unnecessarily rational symbols. But really, overall, we lost nearly 1.5 trillion, in fact, so that is outdated. It was nearly 1.5 trillion dollars from the US stock market from all kinds of tech companies in a couple of days. How did that happen? Well, actually, it happened that in December 27th, more than a month ago already, before this happened, DeepSeek published a model called DeepSeek v3 technical report, or the model itself, DeepSeek v3, and it showed that it was basically on par with GPT-4. A couple of weeks later, right before the crash, DeepSeek published a reasoning model, which basically showed to be relatively similar to GPT-4 or GPT-01, the reasoning model, new reasoning model of OpenAI. So that led to the conviction that with a very little budget, and here in the DeepSeek report of the V3 model, they claim to have only spent $5.5 million for training this model. Of course, they have definitely spent much more because that was one run. They have probably used multiple runs. They have probably tuned all kinds of hyperparameters with different settings before, so they have gained a lot of experience. But still, training this one model relatively cheap if you have the experience. So they didn't make the first step. So that is now an interesting insight. So we can now build all of these things. And this was quite a heated debate the last couple of weeks. So do we need that large compute? Is this age of computation still relevant? But I would claim it is more than ever, because what these models do is they're moving towards much, much, much more compute capabilities and compute demand, actually, because these models spend much less money on training, but they spend significantly more effort on inference now because they're reasoning models. This is called test time compute. They perform more reasoning, they output more tokens to actually answer the same question. So this requires much more compute. So we're even more in the age of computation than we think. There's also a very special form of Jevons paradox, which means that we are increasing the demand of compute if we have cheaper compute. So this model makes compute much cheaper, but we're increasing the demand of that resource very, very rapidly, because as it becomes affordable, everybody wants to use it. And that's another interesting thing is that the whole DeepSeek show is run by a hedge fund manager by a Chinese AI startup. And now there is maybe some incentive to say that was relatively cheap to train. So, but the rest you can think about yourself. Okay, so now from large language models to AGI. And I should have said AHI, artificial human intelligence, not artificial general intelligence, because generally humans are not generally intelligent, but I'll stick to the kind of trendy term, but I would rename it to AHI. So what is this all about? So this is all about a computational structure, these LLMs, that is a very simple structure. It's a transformer network. And this structure is so simple you can explain it to your grandma. But this structure was actually invented to parallelize RNNs or LSTMs at the time that were hard to parallelize on Google's TPU. So Google contributed that structure very early on to science, to humanity. And it turns out that it performs significantly better than RNNs or LSTMs due to the parallel view of the whole input sentence and a feature that's called attention. In fact, the paper is called Attention is All You Need. So it's basically the correlation between words in the input sentences that is very important to get into it. And then there are, of course, some blocks. There's the attention I just talked about. The multi-hit attention block extends at the heart of it. It has a so-called scaled dot product attention, which is a very simple calculation. It's just a bunch of operators, and I don't want to go into too much detail here, but the whole model consists of about 10 operators, and they're extremely simple. But what it does, it takes a tokenized input sentence, for example, transformers are great, and then it produces, in the original version, it was a translator, it produces a translation, like for example, from English to German, transformers sind, and then at the end you can see a probability distribution of all possible tokens in the German language, and if you're a German speaker, you will see it was probably reasonably well aligned with what you would be saying. So now, as I said, you can explain this to your grandmother. They have three very simple kernels: matrix multiplication, softmax, and layer norm. And really 95% of the operations are matrix multiplication, actually more than 95%. And this is why it was a great fit for HPC GPUs, for GPUs designed for scientific computing. Actually, people like Jack Noguera and Horst Simon with the top 500 list had a huge impact in that field, driving computer manufacturers to make machines that are better in matrix multiplication. And it's easy to parallelize, and this is why it was invented by Google at the time. We need to go a little bit more into detail how text is actually represented. Text is represented as tokens, which is an extremely important part. So tokens are really offsets into learned tables or vector tables. So in some sense, you're translating or you're looking up a string in a table, and then you're translating this to a vector. This is all learned. Most common substrings are used in this kind of tokenization, for example, byte pair encoding, but there are many other ways to tokenize. And at the end, it's a quite elaborate, cool mechanism that I don't have enough time here to talk about, but I would recommend looking into tokenization methods that drive this whole field, that basically turn words into vectors. And now these vectors, they can be transformed in algebraic terms through matrix multiplication. And this is how it works at the end. So this was the first breakthrough in 2017. So in 2018, BERT came to the picture. Bidirectional encoder representation of transforms. So now we are looking from both sides. We are omitting a word during the training, and we're trying to recover that word. So it's an unsupervised learning task. So we just omit something and try to recover that. So it's also, you could call it a reconstruction task. It's bidirectional. And it was the first time when we actually saw that these language models were able to develop some kind of semantic understanding. Well, understanding may not be the correct term here, but it learned semantics of words, and it began to see that the context of words actually mattered. Like bank. Is it the bank of a lake, or is it the bank where money is, or is it the bank where you sit on? And these models began to be able to understand, I will just use that term, to what this means, what the context means. And this was a glimpse at the end of the tunnel. Unfortunately for Google, they didn't quite follow up on this much, but very soon after, GPT-2 was trained. At GPT-2, the idea was now that we don't use bidirectional encoding, but we use the future predictive encoding, just a simple mask. It's all close to trivial, these little steps. So they basically mask out all the future tokens and ask the model to predict the future instead of filling in words that have been removed. And now this model was called language models or unsupervised multitask learners. So what does that mean? We could actually now ask various questions that the model has never seen before in any form to the model, and it could complete it correctly. So these questions were all of a nature of a completion nature. So you would, for example, ask the model to complete the sentence, the capital of France is, and then it would most likely fill in Paris. And if you could phrase everything as a completion sentence, these models would be nice and would actually give you the most likely completion in the bulk of language they have seen. This is the beginning of these large language models. 2020, very much the same model was just taken and trained with a larger corpus, which is a larger model. It was just scaled up, more parameters, a larger structure, still the same base structure. And now the paper was called Large Models or Language Models are Few-Shot Learners. What is that? Well, an unsupervised multitask learner is a completioner, but a few-shot learner is a little bit more powerful in the sense what you give it is you give it some examples, like your poor English, good English, poor English, good English, poor English, good English, and then you give it a poor English sentence and you say good English, colon, and then it completes based on the examples it has seen before the sentence. Of course, with the most likely language, that represents the distribution of text on the internet that it has seen. So at that point, it had seen trillions of tokens or hundreds of billions of tokens, and it was quite powerful in representing the statistics in these tokens. But it was still a language parrot in some sense. But what people saw is as we scale it up, as we invest more and more compute, these models became more and more powerful. So what we can see here is the validation loss. So the lower, the better. Like the lower, the more accurate of a representation of the statistics of language the model was. And then here on the x-axis, so these are all going down. Here on the x-axis, we had compute in petaflop per second days. So just as a comparison point, just a couple of years ago, well, nearly 8 years ago, okay, I was part of a project, the Blue Waters project, which was the first sustained petaflop per second computer on the planet. It was a $500 million NSF investment, total cost of ownership over 5 years. So $100 million per year. And that machine would be used for a training task here for 1 day, for 1 complete day. So $100 million divided by 360 days or something, that would be that cost here. But now they continued scaling this. This is 100 days of that machine. So it's already like $33 million in 2008. And this is 10,000 days of using that machine. Of course, they did this experiment later. They had the advantage of Moore's law. They were significantly cheaper. So it's not really clear how cheap that exactly was because it was a private company, private endeavor. But still, it was extremely expensive. But what they also found is that these models, you would increase the quality, so decrease the loss here with more and more tokens seen, so more data. So we needed 2 things. We needed more compute and more data. Fortunately, we had the internet. The internet has tens of trillions of tokens in unique contexts that humans already generated. So they could just download that. Scraping the internet is not a big problem. However, getting the compute was the problem because that was expensive. But then they published this paper, Scaling Laws for Neural Language Models, which now made it clear. Because it said the optimal model size grows smoothly with the loss target and the compute budget. So that means more compute, more model size gives us better results. And that's when people started claiming, this will get us to AGI or AHI, like I would say. This will get us to general human intelligence if you just keep scaling those models. And this is what happened. So now everybody was after the Holy Grail, general human intelligence. Microsoft invested $1 billion, one of the first ones, into OpenAI. I was part of that mission, trying to build these best, most efficient systems while I was there on sabbatical, but also later as a consultant. So we wanted to achieve the Holy Grail. We even had an AI supercomputer comic with our CTO, Kevin Scott, explaining it. So supercomputers were really cool again. The first time that industry actually put up supercomputing or picked up supercomputing as a big field. Before it used to be limited to national and governmental efforts in scientific computing, nuclear stockpiling, and things like that. Now, Google builds a supercomputer. Facebook, a social media company, builds a supercomputer. Tesla, a car company, builds a supercomputer later with XAI, a much bigger machine, actually. So now in 2023, we saw, if you just look at the sales of NVIDIA GPUs, top class NVIDIA GPUs, we saw that companies like Microsoft and Meta were leading the pack. It's not government customers, but it's actually Microsoft and Meta buying more than 150,000 GPUs each. So if you look at 2024, which just ended, Microsoft alone bought nearly 500,000 GPUs. And then the second companies were ByteDance and TensorTorrent, but that has probably ended due to these sanctions that the United States has put up on China. But still, there's a huge competition building these GPUs. So now, Microsoft a couple of days ago just said they're investing $80 billion in AI infrastructure. Much of that is for serving language models and not necessarily training these language models, because serving language models to tens of millions of customers is a much more challenging task than training the one language model on a very large machine. So now it needs to be geo-distributed. Just Trump a couple of days ago also said or launched the Stargate initiative, $500 billion to basically lift the United States, much larger than the Manhattan Project at the time, actually, if you adjust it for inflation. So we will see how all of that goes. Major investment. What is this investment into from a technical perspective? Well, as I mentioned, that's GPT-style models. We want to train a machine to take text off the internet, and we remove the last word here, for example, and you can read this yourself. We run it through the computational structure that I just talked about, the transformer. This transformer outputs a probability distribution over all tokens in the human language. So in this, usually it's something like 128,000 tokens. Here I could only put a handful 7 on the slide just to make it easier to read. But at the end, we know which word we removed. And then what we do is in a training loop, we update all the parameters in this model over and over again in a loop, millions, billions, trillions of times, in fact, to make the model learn the statistical distribution of language. This is large language models. We will soon get to reasoning language models. They actually work differently. So now we train this on the whole internet. Many, many tokens. DeepSeek has been trained on more than 14 trillion tokens here. So that is massive. DeepSeek is also a massive model. The Palm 540B, DeepSeek is 670 billion parameters as a mixture of experts model with only 37 billion active at any inference time. But still, this is massive size, 1 terabyte. So the Palm language model was also, all of these language models takes weeks to train on the largest compute infrastructure that we have. So this is an extremely expensive endeavor at the end. So now, of course, you want to optimize this. And here I want to tell you a little bit about an ancient work of ours, 2019, very, very old. So how do we make these faster? Well, first of all, we realized at that time is extremely expensive, huge industry investment. Then we looked at what was the computational structure, actually. There were 3 computational primitives that were used in this model. Tensor contraction, which is matrix multiplication, statistical normalization, and element-wise operations. Now we could look at the percentage of flops, percentage of operations used for each of these pieces. And it turns out tensor contraction is 99.8% of the operations. So that's something we should focus on. However, people have focused on this for decades already. So this is highly optimized, which means that the 0.2% of the calculation, they actually cost 40% of the time, of the runtime, of the overhead, of the cost of that model. So that's crazy. 0.2% of the operations cost 40%. So what happens if it's not operations? Well, it's all about data movement. The data needs to be moved to the operational units and processed in rather inefficient ways compared to matrix multiplication. So now what we did is we optimized that, or we aimed the optimization or our optimization effort on that data movement, not on the tensor contraction, because people have optimized that before. And we expressed the whole thing as a data flow graph and tried to optimize the whole data movement. We achieved a 30% speed up over standard methods and 8% even over highly tuned methods. So that would be a saving of actually nearly $3.6 million for training of GPT-3. Okay, so how did we do it? Well, relatively simple. You just write down all of these operators and the data flow between these operators. I don't have enough time to explain it, but there's another video that explains it in detail on our YouTube channel, which you can find up here, by the way. So we used our tool, data-centric Python parallel programming, that is called DACE, to look at all different data layouts, look at all different fusion strategies of these various operators. So data layouts, you can transpose the matrix in different forms because at the end it's linear in memory. So you can put it XYZ, ZYX, ZXY, and all the different combinations. In fact, these tensors are typically more than 3 dimensions, so 4 or 5 dimensions. And the different fusion strategies is now which loops do you put together in order to exploit locality. And then we had a very large configuration selection graph that selected the right model. So this optimized data layout and fusion strategies to get to the full BERT encoder and the full performance that we gained at the end. So this is actually in production today. So everybody uses these models. Everybody uses this optimized fusion today. So there is no, it's nothing to be gained. Well, after all, it's 5 years old research, nearly 6 years at this point. But now it became clear that reducing cost is imperative to continue the scaling of models. So now how do we do this? Well, let's go back first. So 2022, or let's go back to our timeline. So now we are in the era of model size scaling. So we made bigger and bigger and bigger models. 2022, ChatGPT came online. It feels like it has been decades, but actually it's only 3 years. It's in fact less than 3 years, where people turned this model, GPT-3, which was not a good conversational agent, or OpenAI turned this model into a nice conversational agent that we like chatting with. And the idea here is to use reinforcement learning based on human feedback, where you train that agent to behave like a well-educated and nice human by basically telling it, you do good, you do bad, you do good, you do bad. So it has lots of answers, and human rate these answers. It's very similar to how we train our children. If our children behave well, they get some reward. If our children behave badly, they may be slapped. So this was really reinforcement learning based on human feedback, so just in a reinforcement learning loop. Later, they got rid of the value function in the reinforcement learning loop, called it direct preference optimization, which is just an optimization to the whole thing, but it's the same thing. So it's really instruction tuning. But now what turned out is that ChatGPT was one of the fastest growing businesses also in human history, because you gave it away for free and it was very useful. How do I now turn this into a business serving millions of customers? That was a problem, because these large models, of course, the larger the model, the more expensive it was to run them. So now we actually needed to work hard on this. It was even accelerated further after Meta decided to open source their model efforts, because they probably saw no way to compete with ChatGPT at the time, because it was already too elaborately established as a market force. They now made everybody on the planet compete with ChatGPT by enabling everybody to build their own models, which was an extremely clever move. Put a lot of pressure on OpenAI, but also Microsoft, for the infrastructure to serve it. So now we compete through openness. What do we do now? You need to reduce costs. You need to train smaller models, better data, more training compute. You optimize these models computationally, and you reduce hardware costs and increase efficiency. So that was quite important. What happened then is we went into the era of data scaling. So from model size scaling, we went to data scaling. We actually wanted smaller models, scaling down the models, but we trained them with more data. By training them with more data, we needed more pre-training compute performance in order to limit the inference compute performance. Right? That was quite important. So now optimization of large-scale compute models determines the future of AI and all the companies. So now that is a key aspect. So how do we go forward? We need a scientific approach to optimizing large-scale training. So I want to give you a little bit of an overview how we improved the cost by nearly 1000x. Just as a comparison point, the DeepSeek model got about a 50 times improvement in a rather short amount of time with very ingenious engineering. But before that, we got this 1000x, which enabled much of the model. So first, we realized that moving data is most expensive. And now, well, you need to shrink machine learning data. And this is also something that DeepSpeed continued. They went from 16-bit floating point training to 8-bit floating point training, which was a great step. But at the end, it's a 2x speed up. So now let me tell you how earlier we went from 32-bit, which was the compute precision at the time, about 2019, 2020, down to actually 4-bit, which is the inference precision that most models use today. So, and the whole reasoning here is brains have limited precision. Why are we computing in FP32? In fact, my brain can reliably distinguish 24 strengths or voltage levels between a neuron. So that's 4.6 bits of information. Why do we calculate in FP32? Well, because SGD, unfortunately, is very hard. So stochastic gradient descent, the learning algorithm, is very hard to control for lower bit widths. And there's a lot of technical detail here, and you can read the latest advancements that came out recently, but let me not get into too much detail here. So now if you have 540 billion parameters, that's 1 terabyte in 16 bits, right? And still 540 gigabyte in 8 bits. So we really want to go lower. Actually, it turns out that rounding to less than 5 bits, to 4 bits, for example, is not so simple. So it requires some foundational insights, but also many, many tricks. So the foundational insights actually come from considering the error landscape. So I'm showing the error landscape, the training or the loss landscape here for one parameter, x1. So here we have the loss, and here we have two randomly initialized starting positions, x1 and x2. Oh no, S1 and S2. And if I'm going down with stochastic gradient descent, I will end up in the nearest local minimum. Here, S1 is slightly worse than S2. But very often in these models, the minima that we converge to are, due to the abundant parameter space, are about the same flatness. So this works quite well because we have many parameters to navigate through the space. Okay, so now you could actually look at this loss function and you could look at the Taylor expansion of the loss function. So your first or your zeroth order Taylor expansion, or first order actually, is the gradient. That should be 0 because you are in a local minimum when you have trained. So we're talking about quantizing models that have been, or compressing models that have been trained to a local minimum. Then it turns out that the higher order terms, the third order terms, they're essentially 0. And that is quite interesting. That depends on your loss function. Essentially, for a quadratic loss function, this is exactly 0. But for many other loss functions, they also are close to 0. So now what matters is the curvature of the error, which many people call the sensitivity. And now if you look at the curvature here in this two-dimensional example of x2, one parameter, and another parameter, x1 here. And we now just draw a gradient plot here, or a contour plot, where the middle is the minimum and it grows to the outside. So now if I ask you which parameter is better rounding, or how do we minimize the error when rounding one parameter, either x1 or x2? So should we round x1 or x2 to the next representable number to minimize the error? Think about this for a minute. Or you could stop the video here. But really, it's x1. Because the idea is that if I'm here, for example, and the next representable number is here, I'm making a smaller error because it's flatter. So you now take this intuition and apply it to 540 billion parameters. To find the parameter with the smallest error, to round it, to push the error you're making into the remaining parameters, actually, that reduces the error further. And so you can write this down analytically, and you keep going like this. Of course, if you do this 500 billion times, that's too much work. It's too expensive. So we, collaborators together with Dan Alistar and Elias Franter, we developed a method called GPTQ that really does that quite nicely. And it's all based on this mathematical formulation. So we really want to minimize the difference between the rounded weights and the unrounded weights, which is clear. That is the optimization goal. And then you solve this post-training quantization problem really by mathematically approximating it. So in theory, you would need to establish the inverse Hessian, which is a matrix of 540 billion times 540 billion if you would actually exactly compute it. But you can't, because that doesn't fit on any computer on this planet. But what you can do is you can approximate it in many different ways. So I don't have enough time to go into all the details here. But at the end, we actually deliver a method that can go down to 2-point-something bits, so easily 4 bits without any significant loss. So that's quite nice. Many practical tools use this method today. So for example, if you're downloading Olama models of the internet, many of those are using GPTQ as a quantization method. Many of those deliver in 4 bits. So this is in wide use. Actually, probably tens of millions of people are using this today, and it had millions of downloads to date. So that's great. So this reduces by a factor of 10, right? We went from 32 bits somehow to 3 or 4 bits or something. It's approximately a factor of 10. How do we now go further than a factor of 10? Well, the second insight is that brains are not densely connected. So why are deep neural networks dense computations? Why is this dense matrix multiplication between any two layers? Well, again, for technical reasons. So we may want to go towards sparse. And the high-level intuition here is that not all features are always relevant, because you can read this sentence even though it's missing about 1/3 of the letters. So that's perfectly fine. And at the end, we can remove many of these neurons, many of these weights, and we can even remove weights between neurons where we are not removing the neurons. And then turns out that we can sparsify many models to about 95%, which makes them essentially 20 times cheaper. So we can sparsify small GPT models and BERT models, so these large language models. However, we cannot really sparsify the large GPT models yet, so we cannot get further than 60-70% without significant loss. So that's an open research problem if you're into it. Don't have enough time to talk about it, but I wrote a very long, together with my colleagues that I mentioned earlier, very long survey on sparsity in deep learning if you want to understand how that works. So that gives you a very comprehensive overview. You can also watch me on YouTube giving that presentation a couple of years ago on the YouTube channel, and again, it's on the SPCL channel we have up here, probably where you're watching that video right now. So now you may be wondering, well, now we get a 20x or another 10x speed up, let's round here, out of sparsification. Can we combine the two? And the answer is yes. So we have a paper that's called a sparse quantized representation that is also enabling near lossless LLM weight computation. So it was at iClear last year. So now we have nearly 100x cost savings or acceleration. Now the question is, how do we now get the other 10x that we promised? Well, we have to go to more efficient processing. It's extremely hard to build more efficient processors because we already have exhausted the bit width. So we used these tricks earlier to build more efficient processors. So with 4-bit processing capabilities, for example, as many NVIDIA GPUs and many other GPUs today, or many inference engines as well from Broadcom and Qualcomm and other companies. But now let's focus on the network for the training devices because they're trained on extremely large supercomputers. They're connected by large networks. Typically, they're connected by large fat tree networks, which are extremely expensive. And these networks are so expensive that they would actually be more expensive than the accelerators themselves if you would build them at full capacity. So that's a problem. So Google recognized this problem, for example, early on, where in the TPU systems, they used the 2D TORs or 3D TORs where you only have nearest neighbor connections. So not a fat tree where you have a hierarchy of switches going up that are quite expensive, covering the whole data center, basically in an all-to-all connected through switches manner. But here they're only neighbor connections. But these neighbor connections, they have problems because if a link breaks, you have to go somewhere else. You have to go another path. But also going from this accelerator to this accelerator needs to traverse many other accelerators, making it quite slow and reducing the overall bisection bandwidth quite significantly. So what we then invented was a mixture of the two. It's what we call Hamming mesh. It's a Hamming graph of meshes. So we use the idea of locally connected networks, but we combine them into or with switches to a larger globally switched network. So you can now vary the size of these meshes. So here are 2x2, but you could build 4x4, 8x16, 4x16, and many other configurations, and then adjust the switch network accordingly. So now you have the best of both worlds. So you can basically get cheap reduction bandwidth, cheap global bandwidth, lots of placement flexibility, very cheap injection bandwidth actually, and getting us to a 10 to 15 times cheaper bandwidth cost than any of today's topologies for deep learning workloads. So this is also quite impactful. So that's the last 10 times. So this gets us to 1,000 times, 10 to the 3. So I would have more to say about this, but I said much of this in earlier talks, and including here, which was a slight repetition. High performance I/O is another one. High performance compute I talked about, and high performance communication I covered some pieces. These are all the pieces that we develop in my lab together with collaborators like Dan to build better compute systems. And if you care about those details, there's another talk on YouTube on the Microsoft Research YouTube channel that I gave last year, talking about these details in much more detail than I had time in this talk. Because in this talk, that was just a side story, the 1000x improvement. But what do we do now? So let us go back to our timeline. Let us go back to 2023. We are still in the era of data scaling. So what is happening now? Well, actually, just at the end of 24, we realized, well, Ilya said it very clearly, that pre-training will come to an end because we have only one internet. We'll be running out of tokens very, very soon. So what do? Well, first of all, we recognize that we have a model already. That's the GPT-4 paper. That's the key plot from the GPT-4 paper, which basically said that LLMs are great knowledge bases because what it shows is each of these bars is a human test. And we compare the performance of the GPT-4 model and the GPT-4o model with human test takers here. So, and this black line in the middle is the 50th percentile. So that's like, we could say half of the humans are worse than this black line and only half are better. And you can see that for the majority of these tests here, and these are English literature and chemistry and I don't know what, so knowledge tests, for the majority of these knowledge tests, language models like GPT-4 are already better than half of the humans. But that's already quite an interesting achievement. So these language models, they have more knowledge than half of the humans. In fact, they have probably more knowledge than every single human. So for sure, they have more world knowledge than I do, and probably many of us. So now, the only unfortunate thing is they couldn't reason well. They couldn't actually solve a task that is not in the language they've seen on the internet. So for example, they can answer what the capital of Cambodia is, which well, Cambodia may not even be a capital, it may not even be a country. But yeah, they could answer all kinds of strange things that I couldn't answer, but they couldn't reason. Because if I asked them to sort a series of numbers, that series of numbers is not in their training data set, so they wouldn't know how to autocomplete it. Remember how they are trained. They're trained to autocomplete. So now we need to make them autocomplete things. But what they have in their knowledge database is how to sort. The idea, the algorithm itself, quicksort or bubble sort, is encoded. So now let's go a little bit more into detail here. What we've talked about so far is actually called basic input-output prompting. So this is how most people interact with these language models today. So we write a prompt and we get an output. So this is great. But if we now give it this prompt, sort the numbers, the sequence, 3, 2, 4, and so on, it would give you a wrong result. The traditional language models today, actually, if you try that, they will give you the right result because they have been using lots of these tricks that I'm going to talk about in a couple of minutes. So there was one interesting breakthrough in 2022, which is called chain of thought. That was quite fundamental. So actually, somewhat aligned with the few-shot learner experience, you could give the model an example. So to sort another sequence, you tell it how to sort it, and then you give it the original task, and then it would actually, so you give it some chain of thought, like how would you do it? Like you explain to a child how to sort, like in the context. And the model itself would now magically be able to pick this up and apply it to the bottom. I say magically because it's still largely unclear how this actually works in these ways, in these activations. So this is quite interesting. And what later turned out that there was a paper, it's called Let's Proceed Step by Step, which literally just added these words, let's proceed step by step, to each prompt, and the language models were significantly better at reasoning. That's crazy, but it's also not too unexpected because now the model already probably has a sorting example in its database. Like it has seen many sorting examples. It just needs to be reminded, hey, look up one of these sorting examples and then do the sorting. So let's proceed step by step. That was fascinating. Then this, of course, took off because there was a new path towards AHI or AGI. So many people now played with different reasoning chains, self-consistent reasoning chains. People immediately invented a tree of thoughts where we could basically split a reasoning chain at some point. So we have a first thought here, which is a set of tokens, and then we split it into two, and then we have another one to split it again, we discard, and so we search through a large space. So what we contributed shortly after was basically graph of thoughts, where the idea is not just splitting, but we could also combine, like in this one, two chains of thoughts or two reasoning steps, which is how I work. If I prove something complicated, I decompose it into smaller pieces, and then I combine these pieces eventually. I solve these pieces separately, and then I combine them. So graph of thought is a very, very important thought process in this way. So we really need to employ that, because if you have just a tree of thought, you couldn't combine any two thoughts. So it's a very simple insight, but very, very foundational to reasoning. So that was our contribution here. So now this whole chain of thought reasoning, so chain of thought, tree of thought, graph of thought is often summarized as just chain of thought. That is getting quite interesting. But now the question is, how do we get to those thoughts? How do we get to those reasoning steps? Well, we could either prompt the model to look it up in itself, or we could prompt the model to be explicit about it and output it and input it in an autoregressive form into its next reasoning. But now, what is a good strategy for reasoning? I gave you one strategy. I give you divide and conquer, like I said. I'm splitting the problem into two pieces or multiple pieces, solve these independently, and then merge them again, like we propose in this graph of thoughts paper. But actually, I want to go back to a very complex game. That is the game of Go. And the game of Go is a very simple game. It requires nearly no knowledge to play. The rules are extremely simple, but it requires a lot of strategy to play. It's probably one of the hardest strategy games that humans have. And it took quite a long time until a machine beat the best Go player. But it happened in 2016. So here the 18 times world champion Lee Sedol was actually beaten by a machine that was running a program called AlphaGo, which was trained on human Go plays, and he was beaten so badly that he literally quit his professional Go career afterwards. So now, how did that move forward? How did that work? So we basically used a Go play. So we represented a Go game here. So we start with the state, and it's just simple reinforcement learning, the initial state of the game. We apply a so-called policy function, and this policy function now outputs potential moves. So here, potential move number 1, potential move number 2, number 3, and we output m potential moves essentially. So now what we do with these potential moves is, well, We have m of those. These are quite many. But now we actually apply a value function to assess the probability of winning for each of those new states that these moves generate. So now, of course, we take the highest probability of winning, and then we play the same game again. We expand with a policy function to m secondary moves. So we apply the value function again, and then we see, oh, this was not a good idea here. Going down, we actually have a better, higher probability here because all further moves reduce the probability of winning, so we continue here. So we move forward, we see this 8% of winning here, so we move forward and so on. So the breakthrough with AlphaGo was that we used a neural network as the policy function and a neural network as the value function. A very simple neural network together with Monte Carlo tree search. This network was actually relatively cheap to evaluate, so we could run 1600 expansions per move, and the depth is decided dynamically. So at the end, it actually turned out that AlphaGo was not the best result based on human input. AlphaZero performed significantly better than AlphaGo. And the difference between AlphaGo and AlphaZero is that AlphaGo was tainted or was trained based on human moves. AlphaZero learned it completely from scratch by itself, and it performed significantly better. So now we could argue that our reasoning may also taint the language models, our human reasoning, to be limited. And now these language models should learn themselves. So that leaves us to thinking models or reasoning models. So how do those work? Very similarly to this AlphaGo approach. So we have this task, sort these numbers. We apply a policy function that outputs new thoughts. So we have 4 example thoughts here, like numbers are blue, which is not very useful. Look up quicksort, oh, that may work, or split into 2 balanced sets. We apply a value function. We see the value function is somewhat reasonable. That's not a good choice, but quicksort may be a good choice. Wonderful. So now we go down, we split it into sets, we pick a pivot, and this is how quicksort works. But now the value function realizes actually for those 6, 7 numbers here, I don't need to do full quicksort. I can actually just do it manually, split it into 2 sets. So this may not be the best approach. So I'm now going here. I split it into 2 sets. It's my next thought. Then, oh, this looks actually correct. This is incorrect because my value function knows there were more numbers and we lost some numbers in the process. And then we keep going. So now the idea here is that the policy function is the deep neural network and it's a transformer network. So it's the expensive network, the language model, large language model. And now the value function itself is another large language model. So basically both are large language models. The value function outputs a value. The policy function outputs a new thought, a set of tokens. So now we cannot run 1600 evaluations of those. Well, we could, but it would be too expensive in practice. So we have to be very, very careful. And we actually look at MCTS chains. So what we could now do is we could employ that during training, during inference, or both. And it turns out that it's extremely expensive to run this during inference, so most people don't. Most language R1, for example, is just imitating it. It's not really running it during inference. They've been trained with these MCTS chains most likely, but actually they use a slightly different method, but a very similar approach. But many other reasoning chains come from these models. So this is now quite interesting. So these are the reasoning models. So we are now moving with what people call strawberry or the reinforcement learning models, as we know in OpenAI, called O1, O3, or many others. We're now moving towards this age of reasoning. And here's an example from Google, so which is Gemini 2 Flash Thinking. So you can actually enter that query and you see it's outputting a lot of reasoning steps. So it's not just answering your query immediately, but it first reasons about it. One thing you can see that it took multiple seconds, 6.8 seconds, as we've seen here, to output that simple answer. And it gives you all kinds of stuff. You're splitting the string, choose a sorting algorithm, apply sorting, step-by-step mental model, and all of these reasoning steps to, at the end, give you the correct sequence of sorted numbers. So this is quite nice now. So these models become pretty powerful with this method. So now the question is, how powerful are they? Well, to answer it, there were several scientists that defined a benchmark called frontier math, a benchmark for evaluating advanced mathematical reasoning, because these scientists got upset that many people claimed that with the GSM-8K dataset, math is solved. Like there were many newspaper articles wrongly claiming this, and they said, well, we are now defining a real math dataset that mathematicians would be proud of. And that's not easy to solve for these parallel language models. And in fact, any of these language models was not better than 2 or 3% in these tasks. So just a couple of months ago, November 24, Terence Tao even said this will take years to be solved by these language models. Well, O3 Preview, a reasoning model it's very similar to the one I mentioned here I explained a couple of minutes ago, got to 25.5% just 1 month later in December 24. So that's quite massive. Now you may say, well, mathematicians is something that's very non-human. It's very computer-like anyway to have these reasoning tasks. So we are still good with our human capabilities. But now I want to show you the ARC challenge, which is defined to test human capabilities, and it's quite interesting as well. So there was basically until the end of 24, there was no progress on this. Also, like less than 5% solved with AI models, but then it suddenly went up. Here you can see the score achieved in these models. And why it suddenly went up, it's because of these reasoning models. It's exactly when they were invented here, and then it went up. And we can see that a good STEM graduate would be at 98% of those, so a smart human. A human who kind of pays a little bit of attention is at 70-ish%, so that's the average mechanical Turker, so they're not necessarily always paying too much attention. And O3 is already better than the average, like not so focused human. So that's quite interesting. Now you may say, oh, I'm a programmer, I'm safe because I'm very creative in my job of programming. Well, I have to disappoint you as well. So O3 actually achieves the 99.95th percentile of competitive programmers. Some people claim in this ELO rating, which is kind of a programming game, some people claim that there was some data leakage, which could be the case. So I'm not 100% sure, but those are the numbers that they report officially. So who knows whether data leaked or not. So we should all see this with a grain of salt, but quite impressive results. And now if you're a scientist in your field, there's a benchmark for graduate level Google Proof Q&A. Human PhDs achieve 34% outside their field and 81% inside their field. O3 achieves 87% in all fields, so it's better than the experts in the field. And again, we have to be very careful about data leakage and various things here. Many of those benchmarks have preventive measures, but the question is how good they really are. So, but is it surprising what we are achieving? No, it's not surprising, because what we are doing is we are using superhuman strategy, the strategy that beat the best human in Go playing, and we are combining it with superhuman knowledge, the database that has more knowledge than any single human. So we combine these reinforcement learners with large language models to develop reasoning language models. And these reasoning language models, they are more than LLMs. They're actually very complex algorithms that move forward. And this is now the era of reasoning scaling. But we are not at the end yet. I actually want to show you an example of the ARC challenge. It's designed for humans, so we will be able to do it very quickly, that the model fails at. And you can quickly solve it. So here we see input 1, output 1. So you train from this as a human. Input 2, output 2. Input 3, output 3. And here we have input 4, and you have to guess the output. And the question you should answer is just, you see each of those examples, we are coloring blocks blue that have been read before. So here in this case, we color 3 blocks. Here in this case, we also color 3 blocks. Here in this case, we color 1 block. The question is, how many blocks are we coloring here? I give you, again, a minute to think about it. Stop your video if you like. I'll not wait a full minute, because you can just stop it. And if your answer was 6, then you're right. And you have been beating O3 as a human, so it's not that hard, actually. So it's another form of intelligence that these models maybe have. So now, if you wonder how this all works from a technical perspective, we've just published a paper on the 23rd of January, led by Maciej Vesta, Julia Ward, and Eric Schreiber, many other people in my group and collaborators, that talks about how reasoning language models are actually coming to play. So how you would train reasoning language models. And it's kind of serving as a blueprint to design these systems towards the future and enable more research into this direction. So it gives you a little bit of idea of the background, the history, some of what I told you about in this talk, gives you architectural details of these models, and then a full blueprint architecture, how you could build your models in a very, very flexible way. So they cover all the models ranging from DeepSeek to what people believe O1 would be, and you can reproduce it as part of that blueprint if you like. So now we're somewhat at the end. So we had these 3 eras, the era of model size scaling, era of data scaling, and era of reasoning scaling. I want to give you some more evidence about these 3 eras actually or based on actual cost of the OpenAI API for 1 million tokens, because OpenAI also went through these 3 eras. So in December 21, we paid about $60 for GPT-3.5. Now, as the model size scaled, the cost doubled. So of course, larger models, more expensive compute. So the cost doubled. So then OpenAI developed smaller models, it was 23, and we can see that actually in this new era, the inference cost was reduced, but the training cost, which is what we don't see in this plot, but the training cost, believe me, was increased because these models were trained with more data. They were post-training quantized, they were post-training distilled. They were actually seeing much more compute at the training side to reduce the inference cost. But now the cost went significantly down to single digit or even less than $1 inference cost per million. And now we have GPT-01 at a $60 cost again. So that was in December 24. So much higher inference and training costs suddenly. So that's unfortunate. Actually, in O3, there are tasks that cost up to $5,000 because you can just run these MCTS chains forever and ever and ever and ever. And that's another problem, of course, if they're getting too expensive. So now what does this mean? Well, what this means, we just need cheaper compute. We need cheaper architectures, like the Maya architecture we've been developing at Microsoft. We need cheaper GPU architectures or even Cerebras. And the principles there are data type, sparsity, and spatial compute. But what we also need, and this is what I talked about earlier, we also need is about cheaper systems, networking systems. So what does that mean? So we could actually look at the switches, look at the interconnect. I've mentioned that earlier with the 10x increase in cost. And here we founded the Ultra Ethernet Consortium to help with that part so that we can basically offer cheaper networked systems. And the principles here are cheap local bandwidth or high local bandwidth, reliability, and of course, cost reduction is extremely important. So here I want to give you a little bit of an overview in the last couple of minutes about how these networks converge, because data centers in the future, AI data centers will be supercomputers. So they will require supercomputer networking. Together with some industry colleagues, I've actually written an early article on this a couple of years ago that talks about the convergence of hyperscale data center and high performance computing networks, which is happening right now. We outlined many features in this, many benchmark results in the Sigmetrics paper, that they're already somewhat converging a couple of years later. And then we found that data center Ethernet and remote direct memory access is not sufficient to solve these issues at hyperscalers. And that led us to the foundation of this Ultra Ethernet Consortium. And I was part of the founders in my consulting of Microsoft. And so many companies built that Ultra Ethernet Consortium or joined that consortium to define an open standard for AI and HPC networking. There's a white paper if you care about the details, but I can give you a very quick overview here. So there are 10 steering companies today, 26 general member companies, 54 contributor companies, and actually now it's more than 1,500 people total. We have physical meetings with more than 60 members on site or 60 people on site. Like this is one of those. I'm actually not in that picture because I'm taking the picture. I'm chairing the session at that moment. I'm a co-chair of the transport working group. So here Karen is my other co-chair. And this is moving very fast. So we will hopefully soon release a specification that enables industry players to build these hardware systems very quickly. So now what is the philosophy? The philosophy is actually that we are not changing the Ethernet PHY layer. So we are also not changing the Ethernet link layer much. There are some extensions, but not too significant. We are keeping the IP layer as well, but we are completely revamping the transport layer. So this is the working group I'm co-chairing that builds the transport layer. There are many sub-layers here that I don't have enough time to explain, but there will be a future talk where I explain those in detail. And at the end, at the application layer, it's compatible with libfabric with some Ultra Ethernet extensions, hopefully running original applications. And the idea is really, we want to enable hardware implementations of an optimized transport over legacy Ethernet to enable vendor innovation, that the vendors can compete and deliver better and better products at cheaper and cheaper prices for everybody. And here's a more detailed view of the transport layer, but again, I will cover this in another talk. I just want to make you aware of this effort. So we could talk about the key features. It's a lossy, or what we call best effort transport, so you don't need lossless networking. We have flexible ordering rules. We have easily configured congestion control mechanism, multipath packet spraying, so adaptive routing at the endpoint, a switch offload, that will potentially come later. Security as a first-class citizen, so really co-designed into the transport and compatible with Ethernet link layer with some optional extensions if you want to make it faster. Actually, security is a very important aspect of it because we know that it has been broken. RDMA security has been broken. So here you can find 2 papers, for example, that outline these issues that I would recommend you to look at. And then Ultra Ethernet fixes all of those. So we could talk a little bit more about the congestion control mechanism, but I want to keep this short because this is currently still in discussion. We're publishing new papers on this as we go, but it's relatively high performance. So it really outdoes everything that exists today in performance, and it is a very nice algorithm that we call SMART, and REPS is a load balancing algorithm. Both of those have been adopted to a large extent into the Ultra Ethernet specification that will be released very soon. Wonderful. So now I want to conclude my talk. So as key points, I told you how to achieve 1000x improvement in cost of these AI workloads. I told you the history about the reasoning language models, large language models, to reasoning language models, to very soon artificial human or artificial general intelligence, having these 3 eras: the era of model size scaling, the era of data scaling, and the era of reasoning scaling now, what many people call test time compute. And it's clear that we will get there because we combine superhuman strategy play with superhuman knowledge and just need compute to make it happen. We need to make the compute affordable. And to make the compute affordable, one component is Ultra Ethernet, the other component is chips that I didn't talk about in this talk, but many vendors are already competing to build the best possible AI chips. So now, if you care about many of these details, there are more talks on our YouTube channel. The YouTube channel is listed up here, and you can also follow us on Twitter or GitHub. You can also follow myself on Twitter or actually X or LinkedIn or Blue Sky if you want to hear more of this. Thank you very much, and